So here's a special Newton's second law problem called the Atwood machine problem. So we have an Atwood machine to the right. Now, usually it will say this Atwood machine has a massless, frictionless pulley. Now, the reason that it has to say that is because when a pulley like this has a mass, we have something called rotational inertia. We'll talk more about that in rotation though. So right now, this pulley is massless and frictionless. Now we have two masses. Mass 1 is 10 kilograms and mass 2 is 2 kilograms. So first and foremost, for letter A, it says, what direction does the pulley move? Well, we know if mass 1 is much, much larger as it is, that mass 1 is going to get pulled down by gravity. Mass 2 will go up like that, which means that the pulley is going to rotate in that direction, which we call counterclockwise. So that's going to be the answer to letter A. Now for letter B, it says, what is the acceleration of the machine? And then for letter C, it says, what is the tension in the string? Now, the key for these Atwood machine problems is that acceleration is going to be the same for both masses. So acceleration of mass 1 equals acceleration, whoa, what was I drawing? Acceleration of mass 2. And then since they're connected by the same string, the tension for mass 1 will be equal to the tension for mass 2. So that's our whole key to this problem here. I'm actually going to write this up here as well. So tension for mass 1 equals tension for mass 2. 1 for mass 2. And again, that is the key to this problem. So because there's two masses here, we have to draw two free body diagrams. So for mass 1, I have my mass 1 right here. We have the force of gravity of mass 1, and then the tension going upwards for mass 1. And I'm just going to put that as tension actually, because we know that the tensions are the same. So I'll just keep it as T. Now the free body diagram for mass 2 is the force of gravity of 2, and then again, tension upwards. Same free body diagram, but these are going to be different. The reason that they're different is because we know that mass 1 is accelerating downward and mass 2 is accelerating upward. So because of that, our coordinate system actually changes. Let me show you what I mean. So mass 2, we'll call up positive on mass 2, but as we go around this pulley right here, that's going to be the positive direction, and then that coordinate system is actually going to flip because of the pulley, and then downward will be positive for mass 1. Now think of this as like a coordinate system like this, but just being bent around that pulley like that. So on this side, it's going to be positive upward. On this side, it's going to be positive downward, because again, that coordinate system that's positive this way is going to be bent like that. All right, so our positive direction is going to be up for mass 2. Positive direction will be down for mass 1. So what we do here now is we apply Newton's second law. For mass 1, we have net force for 1 equals mass 1 times acceleration. Again, acceleration is constant for both of these masses, so I'm just going to leave that as acceleration. And then we get, since down is positive for mass 1, we get force of gravity of mass 1 minus the tension is equal to mass 1 times acceleration. Doing the same thing for mass 2, we get the tension minus the force of gravity of mass 2, because tension is the positive force for mass 2, and then equals mass 2 times acceleration. Now for these, remember, force of gravity is equal to mass times acceleration of gravity, which on Earth is 9.8 meters per second squared. So I can plug that in for our force of gravity as well. So I get mass 1 times acceleration of gravity minus tension equals mass 1 times acceleration. And then here I get tension minus mass 2 times acceleration of gravity equals mass 2 times acceleration. Now for these, I am now going to, let's see what we're finding first. We're finding the acceleration of the machine first. So since we're finding acceleration first, I'm going to solve both of these equations for tension and then set them equal to each other. So for the first equation, we get tension is equal to mass 1 times g minus mass 1a. For the second equation, we get tension is equal to mass 2a plus mass 2g. And now that we know that tension is the same for both, we can set these things equal to each other. So we get mass 1 times g minus mass 1 times a equals mass 2 times acceleration plus mass 2 times acceleration of gravity. Now, since we're solving for A, the acceleration of the system, we want to get both of those terms that have that acceleration of the system on one side so we can factor that out and then solve. Meaning this term and this term, we want that on one side of the equation. So I'm going to do that now. I get mass 1g minus mass 2g equals mass 2a plus mass 1a, solving for, oh my goodness gracious, factoring out that acceleration, I get mass 1g minus mass 2g equals acceleration times the quantity mass 1 plus mass 2. Dividing both sides by mass 1 plus mass 2, we get acceleration is equal to mass 1 times g minus mass 2 times g divided by mass 1 plus mass 2. And now we can plug in our numbers. So we get mass 1, which was 10 kilograms, times acceleration of gravity, 9.8 meters per second squared, minus mass 2, which was 2 kilograms, times acceleration of gravity, 9.8 meters per second squared, divided by 10 plus 2, which is just 12. And we get an acceleration equal to, let's see, 10 times 9.8. Minus 2 times 9.8, then divided by 12, we get an acceleration. Plugged it into my calculator wrong, of course. Acceleration of 6.53 meters per second squared. Okay, so that's for letter B, and then letter C, it says, what's the tension in the string? Now I have two equations that have tension in them, this one right here and this one right here. Doesn't matter which one you use as long as you plug in the right numbers. So let's try the first one. We get tension is equal to mass 1g minus mass 1a. So tension will be mass 1, which was 10 kilograms, times acceleration of gravity, 9.8 meters per second squared, minus 10 kilograms times 6.53. So we get 10 times 9.8 minus 10 times 6.53, and we get 32.7. 32.7 newtons for the tension in the string. Now you can actually check your work here and plug the numbers in this equation, the second equation, to see if you get the right answer, the same answer that you just got for tension, and you should get that same answer.